for the swag today, I am going to talk about correlation in stock portfolios. And you might say that's not a game, but the stock market is kind of a game, so I'm gonna go with it. And this is just a little sort of illustration of how important the idea of correlation is within a stock portfolio. So this will be a fairly simple example, and again, highly relevant to what you're going to be doing in question 1 of Computer Assisted Assignment 3. So imagine that you have a portfolio of stocks, and without loss of generality, we'll just consider 2 stocks. You could have many different ones and then do a similar calculation, but it's a lot easier to visualize with only 2 because it's just easier to visualize things in 2 dimensions rather than multiple dimensions. So we'll imagine that the return on a stock is mu A, and standard deviation sigma A for stock A, and stock B similarly has an average return mu B and standard deviation sigma B. And return here just means the idea of like the amount that it changed divided by the amount that you invested. So just a measure of how lucrative it is for you. And we also need to care about the correlation between the 2 stocks. So that's going to be our correlation rho. And remember, the definition of correlation rho is the covariance between the 2 stocks. So it's the covariance between, I guess, stock A and stock B divided by the standard deviations of each one of them. So the square root of the variance of A and the square root of the variance of B. And the reason that correlation is more useful than covariance, is that it's bounded between -1 and 1. So it's something that you can actually interpret, not just the sign of it, like the sign of covariance could be positive or negative, but covariance can be anywhere between -infinity and infinity. Correlation is nice because it's bounded between -1 and 1. And so the actual numerical value of the correlation is more interpretable than just the covariance. So that's why that's a nice thing to have. So say we have, again, these 2 stocks set up, and we're going to invest a certain percentage of your money in one of them and the rest in the other. And we'll just call that amount, say, alpha. So we'll have alpha of your money in stock A, and then the rest of it, so 1 minus alpha, in stock B. And we want to be interested, of course, then in the average return and risk of the entire portfolio. So this variable P is the outcome of our portfolio. So it's a linear combination, alpha times A plus 1 minus alpha times B. And then we can use all of the rules that we know for linear combinations of random variables to figure out the mean and variance, and hence the standard deviation of this overall portfolio. So for linearity of expectation, we end up with this. So alpha times the mean for A plus 1 minus alpha times the mean for B. And for the variance, again, we're going to get alpha squared times the variance of stock A plus 1 minus alpha quantity squared times the variance for B plus 2 times alpha times 1 minus alpha times that covariance. And so that's again the general rule. If we want the variance of AX plus BY, we know that's A squared times the variance of X plus B squared times the variance of Y plus 2AB times the covariance of X and Y. But remember, we're not given the covariance between A and B, we were given the correlation. So we have to actually like invert this definition here, and that'll get us that the covariance of A and B can be replaced by rho times the standard deviation of A and the standard deviation of B. So that's just taking this and applying it to there. So what we have here, again, sigma A, sigma B are just numbers, and alpha is our parameter. So this variance of P here is just expressed in terms of numbers and this unknown quantity alpha, which we're investing in one particular stock. So what I've got here is just a quick numerical example where we have the return on stock A is 2 and the standard deviation is 0.5. The return on stock B is 8 and the standard deviation is 2. So you can see here without doing any math really that like stock A looks like a more conservative stock, it's got lower return but also low risk. Whereas stock B is something very risky. It has a possibility of a high return, but also a much higher standard deviation. And so the risk, the variance around that 8% return is going to be significantly higher. And then I've also plotted it for 5 different values of rho. and for every possible value of alpha ranging from -2 to 1.2. In sort of normal sense, you would expect alpha to be between 0 and 1, right? You can't like sell more stock than you have, but you actually can. It's called short selling. That's sort of partly related to the sort of whole GameStop thing that just went down. But in this graph, I've included possibilities where alpha is negative or alpha is greater than 1. For your assignment, when you have to do something similar to this, you just have to do between 0 and 1. So let's see what this looks like. Whoa, look at that really cool graph. So this isn't in R, I just did it in Excel quickly, but you could do it in R reasonably well. So I want to focus on a couple of the lines specifically first before we look at the overall shape. Again, remember each one of these lines is for a different possible correlation. So I'm going to put my face back over here. So we want to look at sort of each line individually as its own thing. So first of all, I want to point out here, this point here is stock B and this point here is stock A. We have the standard deviation on the x-axis and the mean on the y-axis. And again, as we sort of looked at from the numbers, stock B up here is riskier and more reward, and stock A down here is more conservative. So less risk, less reward. And that's fairly well supported by financial theory. Like you can't get extra reward without taking some extra risk. Here we also have, let's just examine the line here where it's a straight line. So I'm thinking about this one right here, this line right here. I'm sort of trying to draw it in a color that stands out. There we go, that straight line there. So that's the case where rho is equal to 1. In other words, the stocks are perfectly correlated with each other. If that's the case, then depending on how we choose our alpha, how we choose to invest, we could end up anywhere along that line. So for example, like this point right here is where alpha equals 0.7. Again, 70% of our money is invested in stock A and 30% of our money is invested in stock B. And if they're perfectly correlated, then the relationship between the overall portfolio risk and return is just a linear combination like that. So that will give us the portfolio that we want. If we wanted about a 4% return and the stocks are perfectly correlated, we would invest a bunch of money in the lower risk stock and a little bit of extra of the money in the higher risk stock, and then on average we'd end up with this 70%. This point here. So that's just dealing with when the stocks are perfectly correlated with each other. On the other extreme end, so I'm going to delete those lines. There we go. On the other extreme end, if rho is -1, in other words, if the stocks are perfectly negatively correlated with each other, we end up with this line here. So it's a really weird looking line. Again, just try to emphasize which line I'm talking about here. This one right here. And that is super weird, right? It's like it's a piecewise linear function actually. In reality, you would pretty much never be able to find stocks that are perfectly negatively correlated with each other. It's just, there's too many things that, and in some sense, most stocks are related in some way to the overall market. But if you could find two perfectly negatively correlated stocks, then this line, this sort of piecewise linear function, would be the overall result of your portfolio. And this is really neat because in this example, it means that there's a certain value of alpha, and I think it's alpha equals 0.8 here, where you can get a zero risk portfolio, which is pretty sweet. Like that means that there's basically, as one goes up, the other one goes down. And so you're able to find a portfolio where the return of, looks like here about just over 3% is guaranteed. So you have like a guaranteed risk-free rate of 3% with this particular combination of 80% of stock A and 20% of stock B. Again, it's really unlikely in the real world to have a perfectly negatively correlated pair of stocks, but if you did have that, you could figure out the point where the risk is actually zero, and you could end up with a portfolio that's basically a guaranteed 3% return, which is kind of nice. But then again, like wherever else we go, like we could pick a portfolio like here or there or wherever, but what you would never do is choose a portfolio like this. So hold on, let me delete some of those arrows because they're kind of all over the place here. So look at this portfolio here and compare it to this portfolio here. Both of those have the same amount of risk, about 0.25, and one of them has a more return and one of them has less return. So there is no way you would ever want to invest in a portfolio like this, made up of 90% stock A and 10% stock B, because it's completely dominated by this portfolio here, which has the same risk but more return. So this line here, this like pair of lines, we really can kind of ignore the bottom part of it. So I'm going to just erase this part down here, because we would never want to invest in something that's worse overall, for sure. So kind of the values of portfolios that you might actually consider would be anything where alpha is, I guess, 0.8 or less. Does that make sense? Please feel free to ask questions either in the chat or on Piazza. Because again, any portfolio down here that has lower return and the same risk as another portfolio, you might as well get the higher return for the same amount of risk. All right, so that's the other extreme case where the stocks are perfectly negatively correlated. But again, in reality, usually the correlation is not exactly 1 and it's not exactly -1. It's somewhere in between. So most likely you'll have something like one of these curves that you see here. So either in pink, in yellow, or in light blue. Each of those is a curve for a different choice of the value of rho, that correlation. And for your assignment, here is the hint. Your rho that I've given you in the assignment is negative and between 0 and -1. So I think it was negative 0.25 that I gave you, whatever it is. So your graph that you're going to produce for that part of the assignment should look something like the pink line. That is my hint. Because when we have a negative but not strictly -1 correlation, we end up with this kind of curve that looks like this. We've got this curve, it goes a little bit that way and then this way. So there will be a point somewhere here where you can like minimize the risk. It won't be 0. You won't be able to get the risk all the way to 0, but you can get it as small as you want, sort of find that tangent line or solve for the minimum value of the risk by adjusting your weights, W1 and W2. And then whatever that is, that you could also figure out once you find that tangent line, you can find the return, which is, again, in this example, just under 3%, it looks like. So for you, it'll be different on the assignment, but the shape of your graph should look like this pink curve. So that is my hint for you for that part. Alrighty, any questions about that? I just have a little bit more text here that we can see that obviously that correlation coefficient has a huge impact on the overall risk of the portfolio. But if we have stocks that are extremely negatively correlated, then we can find a particular combination of them that has lower risk than either of the stocks individually, but a higher return than the lowest risk of the two stocks. So that's a diversification benefit that we sort of can, like, if one goes up, the other one might go down, so that kind of buffers our risk a little bit. If it's obviously extremely negatively correlated, then we can find maybe even a 0 risk portfolio, but in practice that's really unlikely. But you could find something that's a combination that you're happy with as an investor, that satisfies the amount of risk that you're willing to take and the reward that you're aiming for, and whatever combination of alpha or W1 and W2 in the case of your assignment gives you the desired return and subject to a satisfactory amount of risk. Alrighty, that's all I wanted to say about this. Oh, I just saw a question pop up on Piazza. To minimize a function over 2 variables, are students expected to use partial derivatives or other tools? So that's a great question relating to what I've just talked about. Remember, the weights have to add up to 1. So you don't need to do any fancy partial derivatives or anything when you only have 2 stocks. If the stocks together add up to 1 portfolio, then minimizing over finding the optimal values of W1 and W2, you can rephrase that in terms of just 1 variable like we've done here. I finally had someone request a topic for a machine learning idea, and it was great. Thanks for that suggestion. If you have any more, there's only 1 more of these, so if you have any more, please let me know. But this is the idea of a Markov decision process. So what I'm going to do is give you a quick intro to Markov chains, like as a topic, which actually are in the course notes. It's in section 9.3, but we're not actually like testing them or teaching them formally in Stat 230. They've been in the course notes ever since I took the class 1,000 years ago, but we almost never cover them. And they're super cool, but there's like entire courses on Markov chains. So it's not something that's part of the Stat 230 curriculum. But if you want to peek at the course notes in section 9.3, then you're welcome to. If you are interested in learning more about Markov chains, again, I highly recommend taking either Stat 333 or 334, depending on your program. And I taught Stat 334 online last term, and so all of my lecture videos are on YouTube freely available. So that might be a good place to start if you're not interested in actually taking the courses, but you just want to get a little tiny peek at them. There's, I think, 6 videos, about 15 to 20 minutes, that cover like the entire Markov chain content. So you're welcome to check that out if you want to learn more. But again, none of this is required for Stat 230. It's just a neat application of the Chapter 9 material. So the idea of a Markov chain is just a sequence of random variables. But there's a couple of conditions. So first of all, the sequence has to be indexed by discrete time. So it has to be like x1, x2, x3, rather than like x of t, where t is any real time. So for example, a Poisson process is not an example of a Markov chain, of a discrete Markov chain anyway, because an event could happen at any time. A sequence of Bernoulli trials could be, because we have sort of like distinct values. So that's the first condition, that it has to be happening in discrete time. The second condition is that the variables themselves, the values that they take on, also have to be discrete. So our first condition is discrete time. Second condition is the discrete random variables. So each value, each xi or xk or whatever you want to call it, xn, has to be a discrete random variable. So it has to have a countable range. And the range we usually refer to as the state space. So those are just like the possible values that the variables can take on. And just in terms of terminology, if xn is equal to I, we say that the process is in state I at time n. So there could be lots of different examples, but essentially we have various states, 1, 2, 3, 4, whatever, and then you can move around from state to state at different times. So you can go from state 3 to 1 or 3 to 4, and like 4 you could go back to yourself, and then like 3 you could go to yourself, whatever. So you can move around from state to state, and those states can mean absolutely anything you like. There just has to be a discrete number of them, so either finite or countably infinite, and steps happen sort of at discrete times. Those are the first two conditions. The third condition is called the Markov property, and I can see where that name comes from. And that is the most often violated assumption. This is the idea that where the chain goes next only depends on where it is now, not on the past history of the process. So not on how long you've spent in a particular state, not on the path it took you to get to the particular state, not on how many times you have revisited a particular state. The only thing that is allowed to affect the future is where you are now. That kind of sounds like an inspirational quote, like your future only depends on your present, not your past, or like, whatever. It sounds kind of silly, but that is the Markov property in essence, that like if we know where we are, that tells us everything we need to know about where we go in the future. We cannot take other information about the history into account when predicting where we go next. So formally, mathematically, what we would say is the conditional probability of going to state J on step n+1, given that we are currently in state I on step n, and given the whole history of the process, all the way back to time 0, we can essentially drop that history. So we just have the probability of going to step to state J at time n+1, given that we were currently in state I at step n. So we're basically just saying we can ignore all of that history. Just forget it. It doesn't matter. It doesn't matter how we got here, just that we are here. And that determines where we go in the future. And so because of that, because the history is completely ignorable, we just call that probability Pij. So this is the probability of going from I to J in a single step. So it's the probability of going, from I to J in one step. And then, of course, we have Pij for each value of I and each value of J, where I and J are states in the Markov chain. And so we can put them into a matrix, which we call capital P, and it's known as the one-step transition probability matrix, which is a long name, very descriptive, that contains the probabilities of transitioning from state I to state J in one step. This matrix P is going to have a few properties as well. It's going to be a square matrix. That's fairly obvious because for every state you could go from, there's a state you could go to, so it has to be a square matrix. All the elements are non-negative because they're probabilities, and all of the rows have to sum to 1 because you have to go somewhere. So like you can't leave the chain. You have to be somewhere within the state space at every step. So if you think about, I am in state I now, where can I go next? You add up all of the places you could go from state I, you must get 1 because you have to be somewhere within the chain one step later. We can also think about what happens in the long term for these Markov chains as well as the short-term behavior. I'm not going to get into too much detail. Again, if you want to watch my videos that are posted, you're welcome to. All of this is bonus content. But there are chains where you'll be bouncing around within the chain forever and sort of moving back and forth between the states. And after a while, it will reach some kind of equilibrium distribution where the probability of being in each state doesn't change from step to step once you've kind of reached a steady state. So it's sometimes called an equilibrium distribution or a stationary distribution, where we sort of reach this balance point where the rate in and out of every state is equal to each other. Or there might be chains where there's one or more states where you get stuck. So those are sometimes called absorbing states. So once you get to that state, you stay there forever. So Markov chains are often used in like an actuarial context for modeling like the state of an individual person. And so like there's like the alive state, and like then there's the maybe employed state or unemployed or various other things, or sick and healthy or something like that. But then there's another state, which is the dead state, that once you enter that state, you can't come back from. So that's known as an absorbing state. And an absorbing state, obviously, in the long term, very long term, you'll end up in one of the absorbing states for sure. And there could be more than one absorbing state. So there could be different places you could end up in the long term. Again, that's very high level. Here's a few quick examples. I'll just sort of also do them one at a time so I'm not overwhelming people. The simplest kind would be maybe only two states. You can go back and forth. That could be things like rain or no rain. That's the example that's used in the course notes. Or like win or loss of a team, something like that. Or when a group did a project on this actually in Stat 334 for me, they looked at the history of elections in the US for different states. And there's two main political parties, so they looked at the probability that each state would either switch to the other political party or stay with the one that they had in the previous election. So you could calculate these values for any set of data that you have. So in this case, the transition probability matrix is going to be a 2 by 2 because there's two states, so we have to have a square 2 by 2 matrix. And we could think about alpha as being the probability of, given that you're in state 1, next time we're still in state 1. And then because the rows have to sum to 1, then this value here has to be 1 minus alpha. And then similarly, if we're in state 2, the probability that we're still in state 2 the next time this happens is beta, and thus this probability here has to be 1 minus beta. So the rows sum to 1, the columns don't have to, so alpha and beta don't have to be equal to each other. And you could, again, estimate those values for whatever process you're talking about. Again, election results is a kind of a neat one application, but there's lots of ideas. Another example is the random walk. And in particular, sometimes we think about the gambler's ruin problem, where you imagine you start with an amount of money, say $I, and on each game, your wealth either goes up $1 or down $1. Because you're playing a game that has this outcome. And the probability of winning is P, and the probability of losing is just 1 minus P, which we'll call Q. And in this particular case, we could imagine that you stop playing once you get to $0. Like if all of your money is gone, you're not going to go into debt. It's a terrible idea. We're gonna stop playing once we get to 0. And then the transition matrix would actually look like this. There's a tiny mistake here. This should be ... There's no maximum value here. So the state space is actually countably infinite, because theoretically, especially if P is very close to 1, if you're really, really good at winning this game, or it's very biased towards you, you could get arbitrarily high values, but you can't get below 0. So our state space here is all of the non-negative integers, and each row of this matrix kind of looks like this. The first row looks like this, where if you're in state 0, for sure you're staying in state 0, so you're kind of stuck there. If you're in state 1, though, you could either go up to state 2 with probability P, or you could go down to 0 with probability Q, but you can't stay where you are. So you could either go up or down, and that's it. And again, that row sums to 1 because Q plus P is equal to 1. Similarly, if you're in state 2, you could go up to 3 or down to 1. If you're in state 4, you could go up to whatever. Sorry, if you're in state 3, you could go up to 4 or down to 2, etc. So we have this matrix that's going to have, like, along the diagonal zeros, along one line above the diagonal are P's, and one line below the diagonal are Q's. And that's going to go on forever. So it's an infinite matrix that looks like this. So that's the idea of the random walk. There's lots of variations of the random walk. So this actually is a variation where we sort of stop at 0. You could have a random walk where you're allowed to go negative as well. So you're allowed to go arbitrarily far into the negative values. And then the matrix would be infinite in both directions. And that would look, there's some neat results for that. We could also put like a barrier at the top. So like, let's say you're a gambler, you start with $I, and then you say, if I ever get to K dollars, set yourself a goal, I'm going to stop then. And then in that case, you have sort of two absorbing states where, like, if you get to 0, you're going to stop playing. But if you get to your goal, K dollars, you're going to stop playing as well. So there's different modifications you can make to the random walk. One last example, this is also actually based on a project that some students did for me in Stat 334, is to look at a tennis match. So if you know how tennis works, once you get to deuce, which is where both players have won 3 points each. Once both players have won 3 points, then you have to win by 2. So deuce is when we sort of start. If a player wins at that point, then they have the advantage, and then if they win again, they win that thing, and then a new game will start. So you have to win by 2. So to get to, if you lose once you have advantage, you don't lose the whole thing, it goes back to deuce. If the opponent wins, then they have the advantage, and then again, if they win a second time in a row, then they win. So we could draw sort of a picture of this. If state 1 here, 2, 3, 4, and 5. So from deuce, you could go to either of these two states. From 2, we could go to 1. From 4, we could go to 5. Or we could go back to deuce from each of those. But once you get to state 1, you're there forever. And once you get to state 5, you're there forever. The game is over and you're sort of stuck there. So that's what the sort of state diagram looks like. And these probabilities here were estimated by like observing a large number of matches from a particular tennis player and finding that, when they were in deuce, they usually won the point and got an advantage 51% of the time, and 49% of the time they lost it. But if they were already at advantage, they had only a 42% chance of winning the point and then thus winning the game. Similarly, if they were at disadvantage, they really felt like they needed to come back and win, and they had a 63% chance of winning the next point and bringing it back to deuce. So that was, again, after observing a large number of matches by a particular tennis player. So this is kind of a really cool thing, because then you can analyze, if you're starting at deuce right now, on average, how long does a game last? You can answer those kinds of questions with Markov chains. And what's the probability that they end up winning overall versus losing overall of their games? So those are just, again, 3 examples of what you can do with discrete time Markov chains. They're really versatile. You can use them for lots of different things. But the machine learning application that I wanted to talk about was the idea of reinforcement learning. So for that, you essentially attach a reward to each state. And that can be, again, how to determine those rewards requires some human intervention to say, like, what are desirable states to be in. And then you could calculate the total reward for a particular path through the Markov chain. And sometimes you want to actually have those rewards just be like the sum of all the rewards that you get on your path through the chain, but you might want to discount them. So something that happens very soon in the future is worth more than something than the same thing happening further in the future. So you could have a discount factor, maybe like gamma, so that each step in the future, it gets multiplied by gamma. And if gamma is less than 1, we're sort of doing a little tiny bit of a discount for future values. And the smaller gamma is, the more we are focused on the present, and the closer gamma is to 1, the more we're focused on like the overall reward over the overall time. It's kind of similar to money, actually. Like if you think about getting $1 a year from now is not worth as much as getting $1 today. So like the discounted value of that future dollar could be multiplied by a discount factor. So again, you could choose that discount factor depending on the situation. So you've got rewards for each state and a discount factor to discount them back to times 0, which could be just 1. And then we don't care about when it happens. We just care about that we get to a particular state. So you could calculate the total reward for every possible path, and then use those calculations, like run lots of different simulations, and figure out what is the optimal decision to make at each step. So given that you're in a particular step at a Markov chain, what is the best choice to make to maximize your future reward from that point? And if you can do that from every point, you can develop an overall policy, which is just a set of rules for making decisions at every step that will maximize the overall total reward. And that's, again, the idea of reinforcement learning. So if you tell an algorithm, these are the rewards for getting what you want, let it do some stuff, and then it's going to try to maximize that reward. And then how you choose to set those rewards will obviously have a large influence on the outcome of the sort of optimal strategy or policy for the algorithm to use. Way early on in the term, I think someone posted a video to someone who had done a reinforcement learning thing for getting their computer to play Mario Kart. So that link is up in Piazza from, I think it was week 2 or 3 maybe. It might have been even week 2. And so that was a really interesting use of reinforcement learning. So they just basically gave different rewards for getting to different points on the track. And so it was sort of trying to maximize that reward by taking decisions at each time that would get the best possible reward at the next step. So that wasn't really a discrete Markov chain thing, but it was a reinforcement learning thing. Alrighty, so that is all I wanted to say about Markov chains in general, and how that ties into reinforcement learning. There's lots more info. Again, if you're curious about Markov chains, you can feel free to peek at the course notes and also peruse my videos that are up from Stat 334. You're also welcome to, if you have any other resources, you want to learn more about Markov decision processes in reinforcement learning, I can maybe find some resources for that as well for you. There was a question about the expected value of the product versus the product of expected values. Oh, that was a great question. So if E of X times E of Y is equal to E of XY, does that mean the variables are independent? No, it does not. You could always cook up an example where that happens to be true, but the variables are still dependent. So it's kind of the same idea as correlation versus zero correlation versus independence. Independence implies zero correlation. Zero correlation does not imply independence. But the contrapositive of independence implies zero covariance is that non-zero covariance does imply non-independence. That's the contrapositive of the original statement. Okay, may I know for computer-assisted assignment question 2E, it says, for probabilities of the different numbers of trucks occurring one day, use the values that you obtained in part A. Does that mean we have to use our own manually calculated probabilities instead of letting the computer randomly generate entries? So because we have a Poisson distribution, you'll figure out the probability of seeing 2 trucks, 3 trucks, 5 trucks, and anything else, like lump those all together. And those are theoretical probabilities. So use those. And those should be the same for everybody, right? Those are theoretical probabilities, not based on your simulated values. Good luck finishing up the computer-assisted assignment. You have a whole rest of your week to do that. Don't forget to make sure that everything is submitted to the Dropbox for the collaborative assignment 2 by April 4th. If you forgot to do something or whatever earlier on, just make sure everything gets into the to be marked Dropbox by the 4th, and then the TAs will mark whatever is in there. And then this computer-assisted assignment is due next Friday. And the final quiz 6, will open next Wednesday and be available until the very last day of classes, which is the 14th. And then, of course, you also know that your final assessment is on the 20th to 21st. So it's open from 4 p.m. on Tuesday to to 4 p.m. on Wednesday, April 20th to 21st. And all the info about that is posted. So there'll be 2 parts, same as the midterm. First part will be 15 Mobius questions. You'll have 90 minutes to do that. And there'll be 2 points each for a total of 15. 2 points each for a total of 30, because 30 is 15 times 2. And then the long answer section, part 2, will be similar to the midterm part 2. You'll get some questions given to you via Mobius. There'll be 5 of them, probably 5 or 6. We haven't 100% decided. But there'll be a total of 70 marks between those questions. You'll be able to go backwards and forwards within them within part 2, not in part 1. And then you'll submit your answers to Crowdmark and Mobius, and you'll have an extra half hour to upload to Crowdmark. And we all are going to be very strict about the time this time. So anyone in the midterm who submitted to Crowdmark more than 30 minutes after they submitted to Mobius got a warning email. For the final, there will not be warnings. You will get marks taken off if you're past the deadline. So you open your Mobius, you have 2.5 hours to work on it, and then you have an extra half hour to submit to Crowdmark. If your Crowdmark submission time is more than 3 hours after you open Mobius, bad news. Don't be in that situation. Make sure you get things in before that deadline. Crowdmark will still be open. You'll still be able to submit late. But if you submit late, you risk disqualifying your entire solution. So please don't do that. Please make sure that you observe those deadlines. And we've given you a huge amount of extra time beyond what you should need, so that if you have slow internet or anything like that, you should be able to handle that okay. Same thing with the screen caps. So now that you've had it done for the midterm, you know how it needs to work. So you open Mobius, take the screen caps of your 5 questions, take them right away so that if your computer crashes, you still have those screen caps. Then you can work on those questions and make sure that when you submit to Crowdmark, you include the right screen cap for each question. And don't forget, because it's just hard for the TAs to mark the questions if they don't know what question you're asking. All right, any questions at all about that? Oh, I see a question. Yes. Can we go through an example of an indicator random variable? Absolutely. Do you have one in particular that you want me to look at? Maybe I'll start off with like a quick review of like what indicator variables are. The idea is like if x is equal to, say, 1 if a occurs and 0 otherwise, then we can have a couple of really quick and easy results. So first of all, if we want the expected value of x, by definition, it's the random variable's value times the probability it takes on that value. So that's going to be 1 times p of a plus 0 times p of not a. But 0 times p of a is just 0 because it's being multiplied by 0, and 1 times anything is just that thing, so it's p of a. So that's the first cool result for indicator variables, that the expected value of an indicator variable is just equal to the probability that the associated event occurs. Similarly, if we wanted e of x squared, we would get 1 squared times p of a plus 0 squared times p of a complement. Well, guess what? 1 squared is 1, 0 squared is 0, so this is also p of a. In fact, e of x to any power is just p of a. And so that means that the variance of your indicator variable is going to be, well, e of x squared minus e of x squared. So p of a minus p of a squared, which we usually write as p of a times 1 minus p of a. So that's the other quick result, that for an indicator variable, all you have to do is figure out the probability of it occurring, the probability of it equaling 1, the probability of the associated event happening, and that instantly gives you the mean and the variance without any work. So all you need to know is what's the probability of the associated event happening, and you instantly have both of those things. The other cool thing about indicator variables is that if we have, let's say, another variable, let's call it y, it's going to be another indicator variable based on a different event, say b, then we can find a cool result for the correlation or covariance rather between x and y. And in order to find the correlation or covariance, we need e of x times y. And that is going to be, well, we think about all of the possible combinations of x and y. I'm going to just draw a little chart off to the side here in a different color. If we have x could be 0 or 1 and y could be 0 or 1, then x times y is 0, 0, 0, or 1, right? Just multiplying through. So the only time when x times y is not equal to 0 is when both x and y are equal to 1. So we can fill this in here, e of x times y. X times y is either equal to 1 if both x and y are equal to 1 at the same time, or 0 in any other case. So it's going to be 1 times the probability that both x is equal to 1, which means A happens, and y is equal to 1, which means B happens, plus 0 times the probability of all three other cases. I'm just going to say all other cases. So that's the tricky thing with those indicator variables. Because each of them is only equal to 0 or 1, then the product is only equal to 1 when both A and B occur. So again, that's just equal to P of A, B. And so the covariance between two indicator variables x and y is the expected value of xy, which we've just found was P of AB, minus the expected value of x times the expected value of y. Well, the expected value of x we found before was P of A, and similarly, the expected value of y is P of B. So this is our covariance for x and y. And that, you can notice, obviously, if A and B are independent events, then this covariance will equal 0, which makes perfect sense. If you attach two indicator variables to two independent events, those variables shouldn't have anything to do with each other either. And that's held up by this, this result here. Okay, so that's kind of like the basic idea of how indicator variables work. Great, thank you so much. Page 232 to 233 example. I will sneak a peek at that. In this example, I'll go up here, give us some space. And it is on page 232. What was happening in this example is we have a bunch of envelopes and they're randomly put into letters. Sorry, exactly the opposite of what I said. You have a bunch of letters addressed to N people and you're going to put each one randomly in an envelope, and we're wondering how many of them end up in the right envelope. So N letters randomly placed in envelopes. And then we want to know if X is the number in the correct envelope. And we want to find the mean and variance of X. So what we want to do in this case, that's a really hard thing, right? The number in the correct envelope is very difficult to find on its own. So we can define some indicator variables. We'll let xi equal 1 if letter I is correct and 0 otherwise. And the cool thing about indicator variables is you look at them and you analyze them individually in complete isolation from anything else that's going on. So xi being equal to 1 says nothing about any of the other letters. All it says is what's the probability that letter I goes into the correct envelope. And if you can figure out the probability of that happening, like this is our event, if you know the probability of that, that instantly tells you the mean of xi and the variance of xi. So we can think about that. What's the probability of a single letter happening to go into the correct envelope? Ignoring everything else that's going on, there's n envelopes, and one of them is correct, so it's just 1 over n. And that's how simple indicator variables are. If you know the probability of the event, you instantly know the mean, and you also instantly know the variance. The variance is just equal to the mean times 1 minus the mean, which is pretty cool. So that's the first step here of, again, considering in isolation of everything else that's going on, what is the probability that letter I, the one you have in your hand, goes in the correct envelope? You pick up a random envelope, The chance that you got the right one is 1 over n. So again, it's ignoring anything else that's happening. And so we get this. But for the covariance, that's when we need to be a little bit more careful. So if we want e of xi times xj, this is going to be the probability that both letter I and letter j are correct. Sorry. And there's a couple of ways to think about this. You could sort of think about, well, if we could think about it sort of like conditioning. So like we get letter I being correct, which is 1 over n. And then we also want letter j to be correct. So given that letter I was correct, letter j being correct, now there's, you have a second letter in your hand, and now there's only n-1 envelopes left, and one of those is the right one for j. So we could have 1 over n times 1 over n-1. That's a fine way of thinking about it. Or you could think about it as like choosing the right 2 envelopes from the other ones in that way. But this is the easiest way to think about it. So letter I being correct, and then letter j also being correct, given that letter I was correct. You're sort of using the the product rule to get this result like this. So the covariance, of xi with xj is what we just calculated, e of xi xj, so 1 over n times n-1, minus e of xi, not variance, times e of xj. So that's 1 over n, and that's 1 over n. Sorry so much for the screw up there. So that is what we have. This is e of x I, and this is e of xj. So we can simplify that a lot easier than before, because we have 1 over n times n-1 minus 1 over n squared. So if we want to put that over a common denominator, we get n squared times n-1 on the bottom. And then we have here an n, and then minus an n-1. And the n's will cancel out. So we just get positive 1 over n squared times n-1. And this is greater than 0. So think about that. Does that make sense? If we know that envelope or letter I is in the correct envelope, does that make sense that it makes it more likely that another letter will also be in the correct envelope? In this case, yes, it does. Because there's fewer ways to screw up. Once you know that you got one right, then there's, it's slightly more likely that the next one will also be correct because there's fewer ways for it to be wrong. If you think about the example that's in the thought question, it's rolling numbers on a die. So if like a particular face I has not been rolled, if you know that no ones have been rolled, does that make it more or less likely that no 2s have been rolled? In that case, it would be less likely, because if you know that there's no 1s, that means it's slightly more likely that there was something of everything else. So it makes it less likely that there was none of everything else. So in the thought question, hint, hint, the covariance should be negative there. But here, it makes sense that it is positive. So we have all the ingredients. We have the mean for each variable, we have the variance for each variable, and we have the covariance for all of the pairs. So the last thing we need to do is use those rules for linear combinations of random variables. So finally, e of x, which is just e of the sum as I goes from 1 to n of xi. We can use the linearity of expectation to say that that's going to be the sum of e of the xi's. And that's just the sum as I goes from 1 to n of 1 over n, which is n over n, which is 1. So on average, no matter how many letters there are, on average, exactly 1 will be correct, which is so weird. Because again, they go in exact opposite directions to each other. The probability is 1 over n, and the number of ways, the number of chances is n, and so it cancels out exactly. And then similarly for the variance of x, which is the variance of the sum of these xi's. We need to use, again, that linear combination of variables. It's not, variance isn't a linear operator, but we know that it's going to be the sum of the variances plus 2 times the sum where I is less than j of the covariances. So that's the formula for the variance of a sum. It's the sum of the variances plus 2 times the sum of the covariances where I is less than j. And then we can sub in those values. So we'll have I equals 1 up to n. The variance of each individual one we had calculated was, let me go find it, 1 over n times 1 minus 1 over n, which is go with that. And then 2 times the covariances. We want to just think about how many terms are there. Here we go, I'll still do this. The sum where I is less than j of this covariance, which we found was 1 over n squared times n minus 1. How many terms are in this sum? There are n. And how many terms are in this sum here, where I is less than j? That's just like saying, how many ways are there for us to choose 2 letters from this pile? Right? We're saying where I is less than j, so we're just going to pick 2 of them and arbitrarily put them in order from the smallest, keep the small one in your left hand and the larger one in your right hand. So all we need to do to figure out how many pairs are there with I less than j is just n choose 2 terms. And so we can then figure that out. So this will be n times 1 over n times 1 minus 1 over n, and then plus 2 times n choose 2. Well, n choose 2 is n times n minus 1 over 2, by definition, over 2 factorial if you like. And then times 1 over n squared times n minus 1. That's going to cancel with that. 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 So we get 1 minus 1 over n plus 1 over n, which is 1. Oh my gosh, that's so crazy. The variance is also 1, which is totally counterintuitive. Like the fact that the variance around how many letters are correct also doesn't depend on how many letters there are is just mind-boggling to me. Like, I cannot think of a good logical explanation for that. The mean makes sense, right? Like, the more letters there are, the less likely each one is to be successful, but the more chances you have to be successful. That makes sense. But that the variance is also unrelated to the number of envelopes and letters that we have, that is just the weirdest thing. So, and it would be very difficult to prove this in any other way without those indicator variables. So I hope, sorry, I've gone over time, but I hope the person who asked that on Piazza is that a reasonably decent explanation? Are there any other things you want me to add to or go back and explain again? Please let me know. That's, again, thank you for asking the question, because a lot of times people do have trouble with indicator variable questions, and I can guarantee with 100% probability that there will be an indicator variable question on the final assessment. If you look at any past exam ever for Stat 230, there is always an indicator variable question, and I'm not about to break that tradition now. So I'm happy to answer more questions about my explanation if there's anything that needs any more explanation. Oh, you said thanks? Great, perfect. Hope that was helpful. Have an awesome day, everyone. Hope you have a great weekend. Good luck on finishing up your computer-assisted assignment and starting to prepare for your finals. And I will see you next week for the last live stream. And then also we will do a final exam review session. We'll pick the date for that later when people know their schedules better. Okay, fab. Have a great day. Bye.